Alright, so today we're going to be doing 6.5 notes, which is applications, and this will be the last lesson in Unit 6. After this, we'll be focusing on the review. So the first thing we're going to be talking about in this lesson, and the main idea of this lesson, is going to be growth and decay rates. So identify the type of growth or decay, or identifying the type of growth or decay, is an important first step in solving real-world applications. Determining which of the three types below will allow you to derive the appropriate model that you will need to lead to a solution. Okay? So there are really three types of growth and decay. There's constant growth and decay, there's exponential growth and decay, and there's continuous exponential growth and decay. Okay? So what we're going to talk about is going to be constant, and this is also known as linear. So this is one that you're probably used to working with. It's basically any linear equation that's going downward, has a negative slope, would be considered a constant linear fixed unit, basically. And this is its equation for growth and decay. So when you get the answer to this, it's going to look very similar to a linear equation that you're used to seeing. So constant is something that's fixed. So this is like you get a $2 raise every week. That's fixed, okay? The next one we'll look at is exponential. So this is the typical exponential function. This is like a growth of 3% a week, okay, 3%, something like that, a rate, okay, a percent or a decimal, some type of rate. And this is modeled like this. Now the rate right here is going to be whatever your percent is, you need to first convert it to a what before you plug it into the formula? A decimal. Yep, you have to make sure you convert your rates to decimals. And decay, same thing. It's just going downward, exponential. The last type we're looking at is continuous exponential, and this uses the natural log called e. And these are the two formulas we use for growth and decay. This is like one we learned about, and I believe it was 6.2, maybe 6.1, 6.2. And it uses the letter E. So when you know when to use this one because we'll always say the word continuous in the problem. Okay, so if you see the word continuous in the problem, you know it's going to be continuous exponential. So now we're going to move into example 1. It says a trash dumpster starts with 5 pounds of garbage. Write the function which represents the amount of garbage in the dumpster after T days given the garbage increases at the following rates. So we're going to look at 3 different types of rates here. So if the garbage is increasing by 3 pounds per day, which type do you think that was? Which type of growth? Constant. Everybody understand why this one is constant growth? Because every single week, it's going to be 3 pounds more. 3 pounds more every single week. If it's a rate, it's going to be, that amount will change. It's going to go up. And does everybody understand why this is growth instead of decay? What word tells me this is growth? Good. This word right here, increases, tells me this is growth. The amount of garbage is increasing. That's constant growth. So once we have that, we're going to use the formula for constant growth. And that formula is A of t is equal to A sub 0 plus R times t. So we're going to plug in what we know. So A of t is equal to, how much garbage did we start with in the original problem? 5 pounds of garbage. And always check, does the units in this part of the question match the units over here? Yes. You always want to double check that and convert so that they match. Plus, what's our rate in this case?
3 pounds.
Good, 3 pounds, so 3t. So as you can see, this is a linear equation. Okay, if you had x there, you would see it as any other regular linear equation. Anybody know what this would be called? Starts with an S. Usually represented by the letter M. Yeah, this is really your slope. And if this is your slope, this is your y-intercept. So this is really just a linear equation. Constant is going to end up giving you a linear equation. So any questions about part A? Alright, let's go ahead and try part B. So this one increases by 3% per day. So what do you think this one is? Good. This one's exponential, and is it exponential growth or decay? Good. This is exponential growth. So we're going to look at the formula for exponential growth on your notes. And it says it is a of t is equal to a sub 0 times 1 plus r to the t power. So now we're going to plug into this formula. So that's going to be a of t is equal to, how much trash did we start with? 5 pounds. 1 plus, what do I need to do with this decimal before I plug it in, or this percent? Good, we're going to turn it into a decimal, yes. There goes me giving away the answers again. Yes, this is going to turn to a decimal. So to get a percent to be a decimal, you move the decimal place 2 places to the left, just like that, to the t power. And this would be your formula for exponential growth. Now typically you want to get this into the most simplified form before you say that this is your formula. So you're going to add the 1 plus the 0.03, which will become 1.03t. So I just combined those like terms there. Does that make sense to everybody so far? Any questions about that formula? Okay. Let's go ahead and move on to part C. So part C says we increase continuously 3% per day. So what kind of exponential model is this one? Or what kind of model, growth model? Good. This one is continuously exponential. So if you see this word continuous, you know you're going to use the continuous exponential model. And is this one growth or decay? Growth. And we know it's growth because they use the word increases. So we're going to set up our general formula. We're going to use the growth formula, which is this one right here. And we are going to plug into it. So it's going to be a of t is equal to your starting amount of garbage, 5, times letter E, which is a number. Remember, E is a number, like pi. To the R, don't forget to convert your R to a decimal, times T. And that would be your final answer for the formula. So, does anyone have any questions about part C? Everybody understand why we used the model we used, why we plugged in and whatnot? Okay. So, now we're going to do some problems where you have to determine and then also solve using these models. So number 2 says, the Smiths bought an apartment for $92,000 that appreciates in value 4% per year. To the nearest dollar, state the value of the apartment in 3 years. So first thing we want to determine is this growth or decay? So the word appreciates is what's going to tell us this. So we use the word depreciate in a lot of problems, which means decay. So what do you think appreciate means? Good. This word means growth. And you can kind of like use context clues to figure that out, right? If one's, appreciate is like more of a positive word, it's going to be growth. So we figured that out. Now we have to determine what type of growth it's going to be. What do you think? Is this continuous exponential growth? No, it doesn't use the word continuous. Does it use a percent or a fraction or a decimal as our rate? Yes. This gives us the hint that this is exponential. So we're going to be using the exponential growth model, which is a of t is equal to a sub 0 times 1 plus r to the t power. And we are going to plug in for all of these different variables. Remember, we're going to actually be solving, so we're actually going to be plugging in for t this time too. So, a of time. Now, always check before we use time, we need to make sure our time units match. Do the units match on the time here? Yes. The time units match. So, a of t So A of 3 is equal to the starting amount, which is $92,000, times 1 plus our rate. So what is our rate as a decimal? Good, 0.04. And then to the t power, and t is 3. So then we just solve this. So this is going to be, remember you just do this in the calculator. So you're going to do 1 plus 0.04 to the third power times 92,000, and we get this. $103,487.49. So do I have any questions about the math here? Okay. Are we ready to move on to the next question? Okay. And another thing I was just mentioning to my other class is if the value is going up, you can check your work by just making sure, is this amount more than the original? Yes. You wouldn't want it to be less, right? Then you knew you made a mistake. So you can always check your work that way as well. So the next one here says Knight Rider Industries bought a $25,000 vehicle that depreciates in value at 15% per year. To the nearest dollar, state the value of the vehicle in 6 years. So which model do you think this one is? Of the 3 models, which one do you think this one is? Exponential, and what kind of exponential? Good. This is exponential decay. So there's a few different clues that tell us this. The value is a percent. They do not use the word continuous. And they use the word depreciates, which means goes down, which means it's decay. So we're going to use the exponential decay formula, which is A of t, excuse me, is equal to a sub 0 times 1 minus r to the t power. So that's the formula we're going to be using, and we're going to plug in for all of the different variables here. So a of, and don't forget to make sure that your rate matches your units. So did the units match? Yes. Yes, they do. So we're ready to move on. So this is 6 years. A of 6 is equal to your initial amount times 1 minus your rate as a decimal. Don't forget. Move the decimal place 2 places to the left, to time as the power. So A of 6 is equal to 1 minus 0.15 to the 6th power times 25,000. And that gives me, remember this is a dollar amount, your answer, $9,428.74. So does anybody have any questions about that? All right. Moving on to the next one then. So this question says, on an airplane, 30 passengers are infected with a virus that spreads continuously at a rate of 0.05% or 0.5% per minute. To the nearest whole number, state the number of passengers that will be infected by the end of the 3-hour flight. Okay. So what do you think this one is? What model do you think this one is? Good. Continuously exponential. And is this one growth or decay? Yep. Continuously exponential growth. So the reason we knew it was continuous because they used the word continuous, right? And this one's growth, so we're going to use the growth model, which is A of t is equal to a sub 0 times e to the rt. Now, there is a problem with this, the units on time, however. What do you notice about the units on time? Good. So the virus spreads at a rate per minute, but the flight is 3 hours long. So can I just plug in 3 for t? No, I have to convert the time of the flight to what? Minutes. How many minutes is 3 hours? 180 minutes. Good. So does everybody understand why I need to convert the flight time to minutes? Okay, good. So it would be a lot harder to convert the rate, so we always convert the easier unit. So that's going to be A of 180 minutes is equal to, how many passengers are originally infected when they go on the flight? 30 original passengers times E to the rate as a decimal. Remember, you got to put another 0 in there because it's it's already a decimal as a percent, so you have to move the decimal 2 places to the left, times t, which is 180. So does everybody understand why the decimal is like that? So then we just calculate this. So this one we haven't done in a while, this calculation, so let me talk you through it again. If you have a phone calculator or a TI-30, this is the process you're going to do. You're going to do 0.005 times 180, and then you're going to hit the E button. So if you're on a regular phone calculator, it's going to be E to the power of X. If it's on one of these calculators, you have to do second E. It's going to be, and when you do that, it's going to come out to be about 2.45. Then you're going to multiply that amount by 30, and that should give you approximately 74 people. Did you guys get that one?
You said do 180 then E.
Oh, you have to do 180 times 0.005. Then you hit the E button. Then times 30.
Yeah.
That worked out better?
No, on the phone calculator it's still wrong. So.
I can come look at it. Let me know at the end and I'll help you with your phone.
It's not like too bad, but it's like it's saying 81, not 74.
Are you hitting LN instead of E?
No, I'm in E.
Okay, let me look real quick. Alright. So number 5 says, in nature, the half-life of a substance is 50 days, not 150 days. Determine the decay rate. Okay. So whenever we deal with something in nature, okay, alright, so when you see the term in nature, this is another time that you use the continuously function, okay? So when you see that word in nature, natural exponential growth and decay models the formula A of t is equal to a sub 0 times e to the rt. But in this case, our rate is going to be negative. Now there are two different ways to deal with this when your rate is going down. You can either make it negative now or you can solve for the negative later. So let me show you how this would work. So the half-life of substance is 50 days, so we have to actually figure out the rate ourselves, okay? So we're going to figure out this rate ourselves by working backwards, okay? So we have A of 50 days is equal to A sub 0 times E to the R times 50, right? Because we have just plugged in for T. So like I said, you can use the negative R here, but we're solving for R, so at the end you can just make your answer negative. It doesn't matter either way. You'll see in the end. So now we have to figure out how much we're starting with of the substance, okay? So basically, we can kind of set this up the way we want to. So if we're trying to figure out the general half-life, we're just going to start with 1 of whatever that item is. Okay, so we're going to plug in 1 for A sub 0 here. So that's going to be A of 50 is equal to, if this is just 1, right, this is 1 times E to the R times 50, so that's just E to the 50R. Okay, so if we started with 1 item, okay, what would we end up with? What would the half-life be? What would happen if 50 days later we have half of it? How much do we have left? Well, we have half of the item, right? So this right here is 1/2. So then we have this to solve. So we have 1/2 is equal to E to the 50R. So what we're going to do here is we have to solve this. So we're going to take the natural log of both sides. This is how you solve for a variable. So remember, when you want to solve for a variable in an exponent, you have to take the natural log of both sides, or the log. But why are we using natural log here instead of regular log? Anyone know? Because this is what? E. So you take ln of both sides, ln of 1/2 is equal to ln of E to the 50R So do you guys remember the power rule with the exponents, with the logs? That's going to be ln of 1/2 is equal to 50R times ln of E. Does anybody remember what ln of E is? Yes.
So why is it 50 again? I mean, why is it 1/2 again?
Oh, it's 1/2 because we're determining the half-life. So basically we assume we start with 1, we'll just pick an amount. You could pick any amount you want. We're just going to start with X amount of an item. I just say we pick 1. So a half-life means how long does it take to get half of that item? Well, half of 1 is 1/2. So like say you wanted to start with 600 of the item. Your end amount would have been 300. So we're just figuring out what half of it is, and that's our end result will always be half of whatever we started with.
So to turn 50 into 1/2, we turn 1 into 1/2.
Oh, why did we turn this into, like, why this turned into this?
Yeah.
So A of whatever this is represents how much we ended up with in the end. If we started with 1 item, we ended up with half of the item. So we can use that to determine the half-life and work backwards to find the rate. So basically, we started with the whole amount of the item, and in the end, we ended up with half of it. We want to figure out how long it took for us to end up with half of the item.
And when you do that, the original 1/1/2.
Does that make more sense now? Yes, exactly.
Okay.
It is kind of confusing. At the end, I can kind of go back and explain through that process because it is kind of difficult to kind of work with nothing. Like you're starting off with nothing, and you have to kind of figure that out. So does anybody know what ln of E is? It's one of the 5 rules that you learned about in 6.3. You can do it in the calculator too if you don't, So you would type in E and ln. It's just 1. Okay? It's just 1. So that just leaves us with ln of 1/2 is equal to 50r. So our goal is to solve for r, so what would I do? Good, divide by 50. And this is where our calculator is going to do the rest of the work. So you're going to type in 1/2, so 1 divided by 2, 0.5. Take the ln of that, so the ln button, and then divide that amount by 50. And you should end up with some rate, negative 0.0139 we'll round it to. So that's our decay rate, okay? So recognizing the pattern, okay? The pattern is we can always find the decay rate of something with a half-life by simply taking the ln of 1/2 and dividing it by t, which is time. So that's kind of what we derived from the problem. So I know this one's a little bit tricky. I promise it's going to make more sense as we practice it. And I'll go through again after lunch and kind of explain a problem like this if you'd like. Alright, are we ready to move on to the next problem? Alright, so we'll do the next problem and then we'll, take a break until lunch. So in nature, a substance doubles every 50 days. Determine the growth rate. So in nature, we're going to use the formula A of t is equal to A sub 0 times e to the RT. And just a reminder that this represents the final amount of something. And this represents the original amount. So they're not telling us how much of the substance we're starting with. We can pick that amount, okay? So let's say we want to start with, we usually want to pick the easiest value. Let's say we start with 1 unit of the substance, okay? And if it's doubling every 50 days, well, we're trying to figure out the rate, so what's the final amount going to be? If we double that. If we double 1 unit, it's going to be 2 units. So that's going to be your end result. So that's really just how you have to think about it. What did we start with and what did we end up with to double it? We want to figure out what the rate is based on the time that it took. It took 50 days for it to double. Let's figure out what that rate is. So we're going to plug into the formula here. This is going to be the final amount is equal to the original amount times e to the amount of time times the rate, which we don't know, which is r. Well, 1 times anything is just itself. Now to solve this, we're going to take the what of both sides. ln. We're going to use the power rule. What is ln of e? 1. What's the last step I need to do here? Good. So the rate is equal to .0139. So what do you notice is different about this one and the last one? This one's positive. Any ideas why this one's positive and the other one's negative? Yeah, this one's growth and the last one was decay. So that one was halving, this one's doubling. But they're doing so, 1/2 is the reciprocal of 2, right? So recognize the pattern. So the pattern of your growth rate is equal to ln of 2 over t, which is time.